Suppose you're doing an experiment on a particular system, and it just so happens that the system follows the polynomial x squared plus 3x plus 5. You define its roots to be alpha and beta and figure out various other aspects about it. But then you notice a different system, something that's its own thing but similar to your previous system. You don't know what that system is like, meaning you don't know what its exact expression is. But what you do know is that this second system just so happens to have roots that are twice as large as your previous one. So what do? You use the sum and product you found in your original polynomial and plug them into the derived form of the second polynomial. What you end up with is y squared plus 6y plus 20 equals 0. Just like that, you'll be solving many other sums where you figure out a second polynomial as long as you're given a small relationship between the roots of the two polynomials involved. Though keep in mind that a relationship between roots also implies a direct relationship between the two variables. For example, let's say one polynomial 2x cubed plus 7x squared minus 1 equals 0 has the roots alpha, beta, and gamma. Then there is also a second unknown polynomial, a y cubed plus by squared plus cy plus d equals 0, with roots that are alpha squared, beta squared, and gamma squared. We need to figure out what the second polynomial itself is. Since the roots of y are just the square of the roots of x, it would mean that y itself is the square of x. And so, we can substitute y into the function of x like this, obtaining this equation. Since this isn't the correct polynomial form, you might be tempted to square both sides to solve this. While it will give you the answer eventually, you'll have to jump through a lot of hoops since this is a trinomial expansion. Instead, you can just send the problematic term to the other side of the equation and then square both sides. Afterwards, it's just a matter of rearrangement. Now in either example, nothing was really out of the ordinary. You might even think you could have solved them on your own without needing to deal with roots. But the convenience of substitution is highlighted most when we need to find sums of high powers of roots, such as s4, s6, s8, etc. For example, if we have the quartic equation x to the power 4 plus x cubed minus 5 equals 0, and its roots being alpha, beta, gamma, and delta, how can we find its s4? Well, if you rely on the previous video, you'd need to create an s equation, or in other words, a recurrence notation, replace S3 and S0 with their respective formulae, and move on. But what if you also had to find S6 and S8? Then it'd be a huge pain in the ass. Lucky for us, it's also given that a different polynomial has the relationship of y equals x squared, meaning all its roots are the square of x's roots. This also means that S2 of x is exactly the same of S1 of y. So if we use this relationship, we can square the entire equation of x and then substitute y into this by halving the powers, thus giving us an equation like this. So now, if we want to figure out S4, which is S4 of x, we simply need to figure out S2 of y. Similarly, finding S6 is just finding S3 of y, which can also be solved very easily. The same thing goes for S8, which is S4 of y. Now you might think you're pretty much done, but there's more to this topic considering the many ways it's used in application. Such as, given that the roots of the equation x cubed plus 4x minus 1 equals 0 are alpha, beta, and gamma, use the substitution y equals 1 by x plus 1 to show that the equation 6y cubed minus 7y squared plus 3y minus 1 equals 0 has the roots 1 by alpha plus 1, 1 by beta plus 1, and 1 by gamma plus 1. Here, the substitution relationship already implies that the roots of y should be these three expressions. So all we need to prove is that the equation of y is indeed this equation right here. And for that, we just need to substitute it. Reorder the relation to make x the subject, plug it into the equation of x, perform an LCM operation and cross multiply. And finally, expand and simplify to obtain this equation. Simple as that. Although, this was just the first part of the question. The second part says, for the case of n equals 1 and 2, evaluate this summed expression. Alright, so we already know that 1 by alpha plus 1 and co are the roots of y. So if we put n equals 1, this expression simply becomes the sum of the roots of y, or in other words, minus b by a of y. As for n equals 2, we get this expression. But this is no different from this expression, meaning this is the sum of alpha squared, or S2 of y. So put in the formula and solve accordingly. Next, Part 3 tells us to deduce the value of S3 of y, which I'm sure you can solve on your own, correct? It shouldn't be too hard if you're one of the people who tested out the sum of alpha cube or cubic equations, but if you're one of the students who didn't try it out, you should know that no, the same formula does not apply to cubic equations. So now, I could give you a formula, but I'd like to keep formula memorization to a minimum over here. So instead, we'll be using the recurrence notation, resulting in 73 by 216, and thus show that this expression is equal to 73 by 36 would be the fourth part of this question. At first, you might be tempted to perform an LCM operation on the left side, but that will only make things more convoluted than necessary. Instead, what we can do is raise each fraction by a single power of their own denominators so that all the numerators are the same. We can then factor out the numerators to get this expression. If you remember our question, this part is S3 of y, meaning this is 73 by 216. But then what about this? Well, if you look at its reciprocal, you'll notice that this is actually the product of the roots of y, which would be minus d by a. If you plug this in and solve it, you get 73 by 36. Naturally, there's more where that came from, and I'll be doing more videos about this if y'all would like more examples solved. So go ahead and link them in the comments below, and I'll eventually show them in a future video. As for this video, the main takeaway would be to understand that a relationship of roots also implies a relationship of the variables, and that when you're trying to evaluate different expressions, try to manipulate them so that you end up with terms that are sums and products of roots you already know. If you're also finding yourself needing help in other topics, take a look at the playlist I've created. It's being constantly updated as time goes by. Or, if you'd like to move on to the next topic, which would be about rational functions, click here for when it comes out eventually. And as always, have a great day and ciao!